So, welcome everybody. Thank you for watching my video. I'm Giovanni Lugaresi from Politecnico di Milano, and today I'm going to present you my work, a joint work with my colleagues Vincenzo, Alba, and Professor Andrea Matta. In this work, I'm going to show you how we develop real-time simulation research testbed. And we developed this testbed with Labscale models of manufacturing systems that can integrate industrial components. So in this video, I'm going to show you a short introduction about real-time simulation in the Industry 4.0 context. Then I'm going to show you the Labscale models that we developed together with the cyber-physical architecture that we developed. Then I'm going to show you also a couple of applications of our approach. So this work starts from the Industry 4.0 context, that is the latest developments of in industry. In industry, we saw a strong push towards digitalization, and we see it's much more common now to find digital instances of products, machines, and even entire processes. And one of the digital models that we can find is are simulation models. And with simulation, it is possible to take a system, a manufacturing system in a certain state, and see if it's possible to optimize certain performances starting from a specific situation. So with a short example, we might have a manufacturing system as such a simple system in which, for example, we have a machine that is broken, that is failed at a certain time, and we might want to use a simulation to understand what is the best thing to do. For example, we might have a couple of options in which we have in one option, it is possible to reroute the products around the failed machine, or alternatively, just send an operator to repair the machine at the current moment. So we might want to use a simulation to understand and to predict what is the estimated end of the day performance. So, for example, the production performance. And then we can use the results to understand what is the best option. And then, for example, in this case, we might understand that repairing the machine would give us a better outcome at the end of the day. Real-time simulation approaches can be tested either on real systems, either with digital models, so coupled with digital models of the system. Usually, if we implement the test on real system, it is possible to implement directly the final version of the algorithm, and we can experience the real interfaces of the system. And this is, of course, it is positive. But the problem is usually that in this case we need to invest a lot of resources, and we need to allocate an entire system for a certain amount of time. And so the risk is that we will spend a lot of time setting up the system rather than concentrating on the logic and the iterations of the logic. Another alternative is to use digital models, but in this case, of course, we will miss the contact with the real interfaces. For example, setting up all the data handling, the connections, the interfaces with the real components, for example, with the PLCs, is missing. And so we will not experience the possible issues that might arise in this case. So in this work, we propose to use Labscale models of manufacturing systems as a good compromise between these two options. What do I mean by Labscale models? In this case, I'm going to show you some models that we made with Lego in our lab. Those are models in which you see there are stations and conveyors the conveyors bring around wooden discs that are tagged with certain colors. The colors identify different part types, for example, and the parts are held in the stations for a certain amount of time, and the time represents the processing time that would represent a real operation. And this type of models allow to use also real industrial components, for example, PLCs, sensors, and actuators that are also installed in real manufacturing lines. In this work, we developed an architecture in which we reproduce the ISO 95 architecture, which is one of the most common architectures in production planning and control. And so we start from the lowest level, which is the manufacturing system, in this case our Labscale models. So the models are composed mostly by machines and conveyors that bring around the pallets, the parts. And we have the logic controllers that in our case are represented by Lego EV3s, the bricks. Then we have software levels that allow us to reproduce the intended logic, for example, the routing of the parts around the system, the priority rules also. And then in the upper levels, we might have other software components, for example, also simulation optimization, and dashboards, databases, and so on. And those upper levels might be also related to other decisions in the company, for example, supply chain management. So here is a little bit more detail on the software levels. We have an execution software level in which we have developed specific classes for all the main components of the system. For example, we have the Lego EV3 brick. We have developed a specific class, so each EV3 in the system is related to an instance, to an object of this class. And in the class, we have methods that are taken from the open source library called EV3 dev. Then the logic level contains similar classes in which we have also added methods to control, to send messages to the real system, and the messages contain specific actions. And the connections between the levels is possible with the MQTT protocol. So we send each level will send to the other level messages containing the specific actions or requirements that needs to be satisfied. So I'm going to show now a couple of applications, and in this application, we have tested the design architecture in a part selector model. In this case, the model is represented here below. The model is intended to send parts to either one of the output buffers. So we have two downstream buffers, and depending on production orders, we needed to send parts to these buffers. What are the parts? The parts are spheres containing a Lego brick, and the parts are identified by the color and the RFID tag. So the system contains two stages. The first stage checks the color of the piece, and the second stage checks the RFID tag. And then, depending on the tag, it will send the parts to the right buffer. If the parts are scrap, so they are not included in the orders, they will be considered as scrap. In this case, I show you also an example of the communication between levels. In this case, for example, we have the RFID sensor that will send us a message containing the code that has been read, and also containing the timestamp, which is the time instant in which the part has passed in the RFID check station. In This other application I'm going to show is a flexible manufacturing system in which we have used the architecture also for a real-time simulation interface. So we have added at the fourth level of the architecture a simulation model made by in Simulink, and the system is a flexible manufacturing system. We have 3 parallel machines that can produce 3 part types. The part types are held in an input-output buffer, and each part has a dedicated slider. And the parts have to be produced by the 3 machines according to a certain production schedule. In this case, I'm going to show 2 different scenarios. So we have in the left, on the left side, you will see the system that has to produce the schedule, and at a certain moment, the first machine will have a failure, and we will use the simulation model to decide how to reschedule the production with the objective to optimize the make span, so to minimize the make span. And on the right, we have the same system, which has been designed just to right shift all the products in case of failures. So now I will let the video start, and you will see in the right case, the system produce parts. If there is any failure on the machines, the system will just wait until the machine becomes available again. So now we see that in both cases we are producing the schedule. The schedule is the same at the beginning for both cases, and the 3 parts are represented by the 3 colors, as I said before. Now we see the first machine has failed at this moment in both cases, and we see that in the left case we have that the rescheduling is ongoing. So we have decided with the simulation that the second part type will be rescheduled on the second machine. On the right, we have simply right shifted the job on the same machine. So we are just waiting the machine to be available again. Now the video will be a bit more accelerated in time, so we will see what happens at the end. We have the left system has finished the production at 6 minutes and 19 seconds. We have finished all this production schedule. While on the right, we are still producing because machine 1 is still producing the first piece. So we have to wait until 7 minutes and 9 seconds to finish the production. So in this case, I show that we have also used the architecture for real-time simulation testing. So in this work, we have developed this type of systems in which we have Labscale models of manufacturing systems with an architecture that allows us to use Internet of Things. So MQTT protocol allows us to interface with real components, and we have also tested real-time simulation in this type of systems. In the next years, we plan to use other models of other systems to test other applications, and we also will open the laboratory as an industrial training platform. So I thank you very much for your attention to this video, and I will be happy to answer any question. I leave on this slide some of my contacts. If you wanted to write me some questions, I would be happy to answer, and or in case we will meet also at the online meetings of the conference. And of course, I hope to meet you all in person, maybe at the next occasions in the next years. Thank you very much again, and have a nice day.